So good morning. Today we will have steady state cornering study extended to cornering study, pure cornering study. So what I mean by pure cornering study, we will have some time varying parameter as function of the parameter which are going to vary as function of time, right? So then it is a complete study of cornering. So we call that as a pure cornering study. In the last class, essentially, we were looking at steady state cornering. In steady state cornering, we were able to derive an important fundamental equation to describe the cornering behavior or handling behavior of the vehicle. And that parameter, the metric is called understeer gradient. So based on this understeer gradient, we were able to describe the tendency of the vehicle. So what is that tendency of the vehicle? The input. Basically, you see this model, bicycle model, what we have studied is a control system model. So it requires some input and it will give you a required output. So under steady state, you would have an input, a steering input, and you would have your response, which are steady state responses. So to determine the steady state responses, we are going to also look at today how can we deduce that from the pure cornering study equations, governing equations. And the advantage of representation of the governing equation into the particular form called the state space form. So that will lead to a convenient way of handling the equation, mathematical equation, and that leads to study and compare different vehicles handling characteristics. So that is the main objective of today's class. So I'm going to share my screen and start lecture. Hope you are able to see the screen. And before starting today's lecture, quickly let us see what we were doing it in the last class. So in the last class, we have just drawn the free body diagram of our bicycle model considered for a steady state cornering. And then at dynamic equilibrium, you could see that the lateral force developed at the contact patch is what is balanced by centrifugal force. That's force balance. And if you are applying moment balance, taking moment at B, you would be able to get FIF, and taking moment at A, you would be able to get FIR. And then since it is steady state cornering, you are able to, the forward velocity U is constant, and you are able to derive the fundamental governing equation. So what do you mean by steady state motion? It is the motion where the motion parameters are not going to vary as function of time. For example, here the motion parameters is U, V, and R. So they are not going to vary as function of time. They are going to be constant. So when you have U and V are constant, the vehicle body slip angle beta is constant. And you have for a particular forward velocity U, for a given steering, you will have tire front axle wheel tires develop alpha F and alpha R. So essentially, the governing equation for steady state behavior study is derived and given by the equation number 15. Delta function of L, R, of course, speed of the vehicle, or you can say U squared by R as lateral acceleration. So it depends upon lateral acceleration and obviously understeer gradient value. So this understeer gradient value can be positive, negative, or zero. Accordingly, we have three important tendencies of the vehicle, and that's what we were looking at it in these three cases. So case one is neutral steer vehicle, case two is understeer vehicle, case three is oversteer vehicle. So we looked at with these three diagrams. One is the requirement of steering angle as function of speed. Another one is looking at radius of turn. So what would happen if I happen to accelerate my vehicle to the turning radius? The turning radius will not change for a neutral steer vehicle. Turning radius would reduce for oversteer vehicle. Turning radius would increase for understeer vehicle. So we have also looked at, in case if we have a vehicle goes in a straight line and you have a side force acting on a vehicle, if vehicle happens to have its understeer gradient value positive, that is understeered effect vehicle, so it will go away from the disturbing force, like shown in this figure. So the side force, wind gust, is acting in this direction with respect to driver from the right of the driver, and the vehicle will go in the left. And if it is a oversteer vehicle, it will go into the disturbance. And if it is a neutral steer vehicle, instead of going straight, it will go at an angle and in a straight line. So that is neutral steer effect. And importantly, we have defined two velocities. One is for a vehicle which behaves an understeer tendency during cornering, given by vehicle characteristic speed. So this characteristic speed is given by the requirement of steering angle when it is doubled as that of neutral steer effect. So then whatever the speed of the vehicle is what is given by characteristic speed, and it is under root of Lg by Kus. This is for a vehicle which behaves understeer tendency. And if it happens to be a vehicle of oversteer vehicle, particularly you see in sporty vehicle or in case of race cars, you see the vehicles are designed for oversteer effect. It requires reduction in steering angle as you increase the speed. And it had happened that when you do not require to give any steering, that means without any steering input, if you have your yaw velocity goes more than 90 degrees, at that time you see that steering zero, what is the corresponding speed is what is given by critical speed. So at this speed, vehicle would go unstable. So this is what we have essentially seen in the last class from the important parameter KUS. So this KUS is basically used for comparing different vehicles classes or of the same class of different variants and so on. So today's lecture number 25, and today is 5/4/2021. Let's look at pure cornering study. Pure cornering. So what do you mean by pure cornering? When I say pure cornering, there are three equations that comes in our mind. One is Fx, expression for Fy, and expression for Mz. So these are the three equations deduced from the 6 equations that we have derived at the beginning of our battle dynamic study. And you see here, these equations are expressed through mu dot plus mrv. Fy is expressed by, this is not plus, it is minus. Minus mrv, and mv dot plus mru, and izz r dot. So equation 1, equation 2, equation 3. So this is basically with an important assumption that the axis set at the CG location of the vehicle are considered to be principal axis. So when you consider that to be a principal axis, what would happen? You would have your off diagonal terms of your centroidal inertial matrix 0, and you would have only mass moment of inertia. And of course, since it is a ground vehicle, the rotational effect, rotational inertia about Ixx and Iyy are neglected, and I have only this equation Mz. So I am not worried about Mx and My. So those moments will come in our vehicle when you consider the suspension also into the vehicle, and it is going to be a transient effect. And a steady state, you would see that this equation is sufficient. So these are all an important sensible assumption, because of which we have these three governing equations here. So in this governing equation, even this equation 2 and 3 are sufficient. Why? Because these three equations are coupled equation. Why these three equations are coupled equation? If you look at fx is function of linear acceleration, as well as you see here it's a product of r and v. R is yaw rate, v is lateral velocity. So you have all these three terms are here, right? And you see fy again v dot ru. So you have all these three terms, and again here r dot, that is yaw acceleration. So these equations are coupled equation. If we are looking this equation and considering if u is constant, my forward velocity is constant, right? But not yaw rate is constant. Yaw rate can change because I give a steering input in a high or moderate speed. I can have yaw acceleration. I can have my lateral acceleration, but u is constant. The forward acceleration u dot is 0. So this term is going to be fx equal to minus mru, where r and u are, if u is constant, v is constant, and r is here yaw rate. So this is an algebraic equation. Equation 1 is algebraic equation. So for u equal constant, equation 1 is an algebraic equation. So when it is an algebraic equation, you see that the equation 2 and 3 depends on r and u value. The equation 2 and 3 depends on r and equation 1 depends upon r and u value. What are those there in equation 2 and 3? Also 2 and 3 depends on the forward speed. Depends on the forward speed. See, you can see here u. Right, it depends upon the forward speed. So in such cases, these equations are coupled equation, and since the equation 1 is going to be an algebraic equation, and these two equations are independent of equation 1, independent of equation 1. So you can say that equation 1 depends upon 2 and 3, as it is the r and v are there. So v and r in this equation, r rate changes in this equation, depends on 2 and 3. Whereas equations 2 and 3, these two equations are function of, or depends on u, right? Depend on u. So where u is forward speed, so u dot is 0. So you see that first equation is an algebraic equation. It is not having a term u, forward speed. So these 2 and 3 are independent of equation 1. That's why these two equations are sufficient for study of pure cornering. Right? Any doubt in this? So I'm going to take now on in our study equation 2 and 3. Right? So let's now look at again our bicycle model. So I have this frame and I have a steering angle given, input steering angle. This is my wheel plane. This is steering angle delta F. And I have here my rear axle wheels collapsed and kept as a single wheel. And somewhere here is my CG location. And this distance is A, this distance is B. From rear axle to center of gravity of the vehicle. This is B. So now this is what you have here. So I would have alpha F. I would have alpha r. Of course, here I would have u and v, right? So let me take that as this is u and this is v, and I would also have here r. So now, what are the forces that are acting here? Since these angles are small, correct? Alpha f, alpha r, beta, and delta f, minus alpha f are very small. That is low angle turning. That's called a low angle turning. At high speeds or moderate speed, the steering angle input is very less. So you can call this assumption or this state of motion of a vehicle as low angle turning. So since they are like that, I am going to have my forces here represented by Fy r, and here Fy f, and I would have here my centripetal force here. But here, see, now this is going to have r as well as v dot. Both are there, right? So it is not constant. So that's going to vary. So I would have mv dot as well as r dot terms. So I would have here, this is v. So I will have v dot as well as this is r dot, right? So let us just write 1 minute. Just a minute. Let me put now here this equation. Because of that, it is it is this first equation. So I will have here mv dot plus mru. Earlier what we had is mru alone. So now we have mv dot plus mru in this direction. So this is what is my free body diagram. And this term comes here is to bring in a centrifugal force component, as well as r and u. If you look at, that's what is Coriolis component, right? So these terms are brought in here for dynamic equilibrium. So now let's write our first equation here as this. So what is my Fy? So Fy is equal to Fyf plus Fyr, and that's what is equal to, this is minus. So if I consider this side as positive as per the SI coordinate system, and minus, so this is what is minus, and that goes on the other side. So it is mv dot plus mru. So we know Fy f as minus C alpha f into alpha f, Fy r as minus C alpha r into alpha r in SI coordinate system representation. This minus sign is not referring to negative stiffness. There is no negative stiffness. So minus sign here is to account the direction of alpha f and alpha r. That's why I also represented here this direction. So these angles are measured in counterclockwise sense in this. And in SI coordinate system, clockwise direction measurement of angle is positive. That's why these minus signs are there. So if I take that here, I would have my equation written this mv dot plus mru equals Fy of this minus C alpha f minus C alpha r into alpha r. So now alpha f and alpha r from the bicycle model, I know already we have derived that in terms of steering angle and this. So here, how do you get this alpha f angle? So what is the expression of alpha f? So let us substitute that here. Minus C alpha f value is delta f minus, because delta f minus AR by U minus AR by U is this because of this is the point of rotation, and A into R would have linear velocity. That along with I have V also, so V by U. So this is what is delta F. You could see that in our two lectures before we have derived these expressions, minus C alpha R into on this. So here this is all minus of this. This is what is minus alpha. So minus into minus become plus here, and here alpha R when I substitute again that minus sign I take out and this become plus, and BR by U minus V by U, right? So this is what is equal to mv dot plus mru. So this mru is again an algebraic term, can be brought on this side. So you'll have mv dot equals. So this is taken on the other side. So how do I write this? Is now see, I will take v and r and delta separating, right? So I will have coefficient of v written now. So here it's MRU that goes on that side. So coefficient of V to write, you see minus C alpha F here, and here minus C alpha R. So minus sign if I take out, C alpha F plus C alpha R by U into V. Then let me take coefficients of R altogether. So here R, if I multiply minus A C alpha F by U, here R minus plus B C alpha R by U. So I will take that minus A C alpha F by U plus B C alpha R by U into R. And then I have steering angle term. So that's going to be plus C alpha F into delta F, and this MRU is brought on this MRU. So this is at R, so I should take it along with this, right? So now what am I going to do? Instead of that, I'm going to divide this entire equation by mass. So if I do so, I would get V dot, that's going to be minus C alpha F plus C alpha R by MU into V plus within bracket minus AC alpha F by plus BC alpha R whole divided by MU. And here I have again MU. So so this is divided by M. So I will have minus U into R plus C alpha F divided by M into delta F. So that's my equation number 1, Roman letter 1. So this is what is that differential equation, single degree first order equation. So it is not having V double dot, right? It is V dot. V dot is what? It is the rate of change of lateral velocity. So it is the lateral acceleration expression. So you have this, but it is function of lateral velocity as well as R for the given steering input. So you have this is a coupled equation. So this is equation number 1. So similarly, now to get that another equation of the second degree of freedom, which is motion, I'm going to take moment now, right? So let me use that second equation. So M is that, this is what is I z R dot, which is equal to, I'm taking moment at its CG location. So what is the moment? Positive direction moment. Clockwise is positive. So F into A. F into A is what? Moment by front axle lateral force moment at CG location minus FB R into B. Why here minus? It is counterclockwise moment. In SI system, coordinate system, it is negative. So by substituting now this again, C alpha F into A minus C alpha R into B. I would continue this, substituting for alpha F and alpha R, which we have already got the expression. So this should become, so that what expression I had is minus of what is there here, delta F minus AR by U minus V by U, what is written. So minus into minus become plus. So C alpha F within bracket, it is delta F minus AR by U minus V by U into A minus C, minus into minus become plus, C alpha R within bracket VR by U minus V by U into B. So this is what is I Z R dot. So now I have to write this first order equation. So R dot I require. So I can take this down and group them as coefficient of V and coefficient of R. So therefore R dot is going to become, so here I am going to group first with V. So minus C alpha F A by U by I Z. And here again I have minus C alpha R B by I Z U. So if I combine that, I would have minus A C alpha F plus B C alpha R by I Z U. And this would become coefficient of V plus, then group all coefficients of R terms. So here I have C alpha F A by U, and here I have C alpha R B by U, B squared by U, here A squared by U. So I will have this minus C alpha F A squared minus B squared C alpha R by I Z U into R. And of course then one term left is input term, so that is plus C alpha F into A. So A C alpha F by I Z into delta F. So this is my Roman letter 2, equation number 2. So now look at these two equations. They are very interesting equation form. So I can write that in this convenient form. I can represent this equation 1 and 2 together as this form. So how am I going to represent? I can take first equation and second equation, which are there on the left hand side, V dot and R dot as a vector, V dot and R dot as vector on one side, and I can group here as a matrix where the 2 by 2 matrix where the elements are written like this. So minus C alpha F plus C alpha R by mu. So that is this term. And what is coefficient of R here? This, so minus AC alpha F plus BC alpha R by mu by mu, and I have minus u here as well, minus u. So this is my second term, and this is going to be 2 by 2 matrix. So first row is written, second row I should look at this. So minus AC alpha F plus BC alpha R by I Z U, and here minus C alpha A squared C alpha F minus B squared C alpha R by I Z U. I Z U. And you see that I'm going to multiply this matrix by a vector where those vectors would have two parameters. One is lateral velocity, another one is yaw velocity. So if I multiply this matrix with this vector 2 by 1, what do I get is first row into this. If I multiply, I'll get first equation, v dot equals this. And of course, this term, input term, I have to get. So delta f, if I take it out, and I will have this as a vector, where first element is C alpha f by m, and second vector is this A C alpha f by I Z into delta f. So now this is my combined equation. I could combine equation 1 and 2, correct? So if you look at this, I can rewrite this in a condensed form, q dot. So what is q dot vector? That is 2 by 1 vector, where that elements are v dot and r dot, and that's equal to, I will call this matrix 2 by 2 matrix as A matrix, 2 by 2, and I'll call this vector now as q vector, because v, r are q vector and their first derivatives are on the left hand side, plus I will have this input vector as small b vector into delta f. So this is what is the popular representation called state space representation. State space representation. So I have two governing equation for my vehicle right here. So equation 2 and 3. These are the two governing equations required for my bicycle model for pure cornering. Why we do not consider equation 1 we have seen, because these two equations are independent of equation 1. As is equation 1 for a constant speed, when you consider, is algebraic equation, and this 2 and 3 is going to be independent of this equation, right? Where equation 1 depends on equation 2 and 3, as r and v, you get it from this equation 2 and 3, which you have just now seen. So because of this, and we can consider only equation number 2 and 3 are sufficient for pure cornering study. And with this low speed cornering, low angle cornering, that would normally happen moderate or high speeds, you would have your governing equation is represented by this form. Why? Because basically this mathematical equation is to have a control system design. This is useful for control system design. Control system design, right? So you see there is an input term, you have this and this. So there is also an output equation that we will see later on. Now, how this equation is useful? So I can get my steady state responses from this equation. By having this, I can get what do you mean by steady state responses? What are steady state responses? What are steady state responses? One is yaw velocity, this lateral velocity response, yaw velocity response, third lateral acceleration response, fourth you also have curvature, so curvature response, and fifth side slip response. Side slip is beta, so side slip response, side slip rate response. Side slip or side slip rate? Side slip response it is. Side slip response. Side slip rate is beta dot. So side slip response. So what do you mean by these responses? These are called steady state responses, or they are called steady state gains. So steady state gains. All right. So you can also say they are a transfer function in Laplacian domain, right? So what do you mean by this? These responses, if I can have these responses to compare different vehicle handling characteristics. And the characteristic parameters or responses are these 5 that what are listed, right? So these all can be easily, readily found out from this state space matrix. And I can also find out stability analysis. I can do a stability analysis. For that, I need to have my input to be equal to 0. So when I make my input equal to 0, then it is free response study. So in free response study, I would have my equilibrium is ensured or not. So stability analysis to do, you would ensure that the steering inputs are 0, and then you would go for analyzing it. So like this, you see that this state space representation is quite useful form. So let us now continue with how do you find out this state space response, this steady state gains from this state space representation of bicycle model. So let me stop at this moment, this recording, and then again I will go for the next period lecture.